Audible? So my topic was TianGO science space, and we named it as science potentials of the space-based Deci-Hertz Gravitational Wave Observatory. And I displayed the paper based on which I have found this presentation. The main aim of this topic is to be able to cover the full band of gravitational wavelengths. So to have something sort of a gravitational, multi-gravitational wavelength astronomy. This is a very typical image which a lot of you may have seen by now. But I have highlighted here the Deci-Hertz band, which has not been covered so far. And what I wanted to emphasize here is how many of the sources are falling right within that band, from at least either side or right at the center of it. So the prime motivation, therefore, is to be able to cover this band because I found it to be extremely rich in its science potentials. It is very rich in physical aspects, astrophysical aspects, cosmological prospects, and it is completely, the data from this band is completely absent so far. This is another slide which is often shown, which again gives you a feel for the type of sources which can fall into this band and how rich it is. So right now, we have ground-based detectors. This paper assumes Voyager design sensitivity. And these are the three: LIGO, Hanford, Livingston, India, and the Virgo and Cabral. So it assumes that the ground network is basically made of these 5 detectors. I had also come across a LIGO Australia in one of Sanjit Mitra's articles in one of my college magazines, but they have not assumed it here. And
no, it's not like unfounded. It's not progressive.
So these are the 5 detectors that form the ground-based. Then
Just for information, that Australia proposed a detector long time ago, much before India, but it did not. They did not have funding, and at some point there was a discussion whether there should be a detector in India or Australia. So there was a plot which was made around 2008 that suppose you have these detectors right now, 2 detectors in US, and there is one in Italy. What is the optimal location for putting the next detector? And that was right in the middle of the Indian Ocean. Obviously, you would not to go there because it would be much more fun. But so the places which were nearby was India and Australia. But then India was chosen. Even though Australia was slightly better than India, location-wise, but it is not just the location which determines the detector. It is about people, money, all the communities drive, many things are involved. So which India won hands down because obviously there are many reasons. Many reasons, meaning the obvious result is that it did not win very quickly in Australia, but that did not happen. So that was the main part. But after that, after LIGO India adopted, of course, there was no point in pushing Australian detector because they are. But now again, there are activities going on to see next generation if they can contribute, or there is a cheaper option which may be possible to detect only the at a very high frequency range. There is something called a NEMO configuration, which can detect the high frequency emission after the merger from neutron star, and those things people are exploring. But right now, at a kilometer scale, there is no proposed Australian detector.
The ground configuration is made up of the LTK configuration, and they've added an India. And the space missions which are there, the ones which we might be familiar with is the Milli-Hertz mission, LISA. There are also 2 Chinese missions, TianGO and Deci, which have been proposed. And then at the Deci-Hertz front, there were certain missions proposed, but I think they have not been approved yet. So there's Big Bang Observer, Deci-GO, Deci-GO, and Deci-GO. And especially, I think Deci-GO has 12 satellites. So yeah, that's
final
at this point. So a more working solution is going with this has been proposed between an American and Chinese collaboration. They are proposing a new detector called TianGO instead. Its sensitivity can be upgraded by about 10 times later on by going to TianGO. But right now, this is the paper. In this paper, they have tried to discuss that. I think even the Indian effort is trying to add to it. So, but I'll get to that later. The main focus is on TianGO, and if you see this slide, then this is the main plot that shows you the promise of this detector. I have shown the purple curve corresponds to LISA, the dark blue one in the center corresponds to TianGO, and the orange curve corresponds to advanced LIGO configuration. And the initial GW30914 signal has been shown in a dotted pink curve. So one can see that LISA would probably not catch such signals. LIGO definitely will, but a lot of the signal also lies in the decihertz band, which will be completely missed out. So right now, the dark blue curve, TianGO will fill that gap in between and also supplement LISA and 8 LIGO observations. So it fits right in between. And later on, with upgrades, that sensitivity can be further increased by going to TianGO, which is the red curve, and then the DeciGO configuration. This plot may mislead you into thinking that in the millihertz band, some of the decihertz detectors might have higher sensitivity, but I think that extrapolation should not be taken into consideration. So across those curves over there, just focus on the middle part.
I would not believe that extrapolation. It is like almost every frequency they have sensitivity. It's very difficult to predict. Something will go wrong.
To give you an answer in the beginning itself, because it's a paper presentation, papers typically have abstracts and conclusions being read at first. So I'm giving you all the science potentials in one go in this slide. In the first table has a summary of the TianGO science cases. In the paper, they've enlisted, that is the table which I've copied from the paper, but I found that list to be slightly incomplete, so I've added in 4 from my own side. So that is the summary, the science objectives, the possible targets that one can have, the information one can extract from such sources. But in the conclusion section, we have also mentioned 2 extra, which is that in addition to these science objectives, which I will discuss in detail later on, they also mention that decihertz band can also possibly detect the GW memory effect or test the angular distribution of memory background. It can also, if intermediate mass black holes are detected, then it can also probe ultralight bosons via super radiance. And I think in the GravSat meeting, Shirke had mentioned slow pulses. So I've added that from my side. And there's a very teeny tiny possibility that CMP might also be detected, possibly, but that might be like
the primordial background. Primordial.
Yeah. So I've added that in, but that might be slightly ambitious. So to conclude, if you want to go over the conclusions, then I think the first few lines summarize it very succinctly. We will have a combined network of both ground and space-based GW detectors, and the scientific rewards would be greater than the sum of its parts. This would be because of the very large baseline that will be achieved, along with having combining all the detectors coherently, which is why you require a space-based, both space-based and a decihertz detector. So together, I think all in all, if I were to summarize this topic in one sentence, then I would say that this is science potentials look tremendously exciting because the decihertz band has its own standalone benefits, but it can also supplement LISA and LIGO. Okay, so go into further detail, I think.
There any astrophysical source that is primarily Asian, not possible in other
Yeah, I will get to it. I think, for example, the type 1A supernovae, which was shown in the initial diagram, they fall right completely within the decision. So these are some science questions from more science point of view rather than focusing on the detector. So from the science point of view, these were some questions that I myself had for a long time, even before the topical course began. Over the past few years, I realized within GW, I particularly myself had these questions. I would see over 2 years, sort of this was the picture I had in my head. I see early warning in red. It transitions to black towards source localization, and then source characterization and parameter estimation is completed. So thanks to this assignment, I was able to fill this, and I kept this aside for my own self-study. And because of the course, I was able to read it properly. So I was able to fill this in completely. This is like the one slide which I might like to summarize the reading assignment with, but I'll go into, like, it can be slightly overwhelming, so I'll go into it part by part. But this is the one single slide summary of the promise of the science prospects of the Deci-Hertz band, namely early warning, source localization, the variety of sources that it can observe, and which can serve both cosmological and astrophysical promises. And then the corresponding parameter estimation, and again the science that can be derived after getting to know those parameters. So from this point on, I will go into each of these one by one and see how the questions can be answered. But from this point on, I'm not sure about the time part. So whenever you want me to wrap it up, I can terminate my presentation. So some of the details, because it's very rich, it was a very dense paper. Some of the details will be covered in some of the other topics which were identified for this reading assignment. So you will hear about these in other presentations, but I will leave it to those speakers. And I will stick to those which will not be otherwise covered. Within the early warning part, the Deci-Hertz band can first of all provide early warning days and weeks in advance. These can provide early warning, but that goes years in advance. Deci-Hertz is perfect because it gives you early warning days and weeks in advance. It can probe the early part of in-spiral, which is otherwise invisible, and it can also probe precursors of certain mergers, especially in case of precursors that show up in the high energy band, like short GRDs, fireballs, and even fast radio bursts. So these could be studied with Deci-Hertz. Next is some of the source localization part. Because of this early warning, because the Deci-Hertz band is separated both in frequency and it provides a longer baseline because it's also separated in space. So it results in a longer baseline hybrid network. And in case of mergers that might have electromagnetic counterparts, it can help improve the source localization. So like aid multi-messenger astronomy. To give you a feel for the source localization part, how it will be better and faster, this plot shows, I've shaded the section that corresponds to the Deci-Hertz.
So it's early inspired. So if you go to a sensitivity curve, so that sensitivity lies above, like advanced level is much lower than the Deci-Hertz.
Okay. That's TianGO.
So how inspired before inspired the signal is very weak, not like the inspired. So is it like physical to be a practice?
First of all, I think that signal was lying above the sensitivity.
Okay, so
Would you like me to pull that out?
I understand. This is
It shifted in frequency, not in
the frequency, not in the time. That is the right. That is the answer. In time domain, it looks like the frequency, the amplitude is lower. But in frequency domain, because they spend much longer time than the amplitude, actually SNR is always higher in the lower frequencies. It's completely counterintuitive. But okay, maybe you can show that curve one more time. It's that plot, it is a dashed line, that is the proper spectral density for the. Yeah.
It's a small piece of basic and then that can follow that.
Yeah, meaning it is like even in the light of band also, because the binary spend much longer time in the lower frequency, even though the amplitude is actually smaller there than the final merger, that chart signal is misleading. The chart signal is misleading because it shows that that with time, amplitude and frequency both are increasing. So it feels like the amplitude will be higher there, but the frequency wise, actually the signal spends much longer time in the Lord. I mean, if it spends equal amount of time, this would like the curve would be like this. It will increase its frequency, but it spends much longer time in the lower frequency, so it actually goes like this. That's the main reason. That's why it falls like f to the power minus 7/3. Minus 7/6 or 7/6 in the amplitude.
ESD is minus 7/6. PSD is 7/5.
PhD is 7/3. This thing is up here, minus 7/6.
Somebody asked in the chat if you could ask the question.
Ask her.
Hello. Hello.
Go ahead, we can hear you.
Yeah. Thanks, Parisee, for showing this slide. Actually, I wanted to ask something regarding this. One second. Okay, so I wanted to ask something about. You see this TianGO, the bluish curve, right? So this y-axis is the sensitivity, right? Okay. So Sanjit, when binaries, compact binaries are observed, they're GW signals. So they are observed in this frequency band of around 100 to 100 and greater than 100, somewhere around that, right?
It's shown in the it is there. Like see that. I think Parisee can just show it with the mouse. Then it is shown that track is shown.
Yeah. So I was wondering. See, so when I read this paper that given by Banashud that you gave me, right? So there they mentioned that okay, binaries can be observed around 100 hertz frequency and till 100 MPC. So if like TianGO will have higher sensitivity there. So if now because of this higher sensitivity, what will happen? Binaries to even greater distances, because their signals will be redshifted, so they will have to be observed in higher frequencies. Sorry. I mean, higher lower frequencies, right?
That is right, but I think the redshift part, see, this is one order of magnitude, so you will have to have binaries at redshift 10. Like that would be a bit unlikely. I will see binaries at redshift 10 because the star formation etc. happened quite late.
Yes. Yeah. So that means most of the binaries will fall somewhere around this only, close to 100 only, right?
No. That what I mean is that the scalar mass which are marked in that band. But in TianGO band also there will be mergers. I think Parisee already mentioned about the intermediate mass black hole. They will, so few hundred solar mass ones will merge in TianGO. In fact, there is a problem that because of redshift, those few hundred ones actually go to few thousand ones equivalent. So then they actually enter the Lisa band when they are at higher redshift. The intermediate mass ones which are nearby, like shift of 2, 3, those will be in TianGO.
Yeah. I'll have to once again check the formula of how mass dependence is on the existing frequency. Because what you are saying is again like order 2-3 difference because of mass only. Is it? Sorry if I'm not making much sense.
No, not just mass, meaning this here is no, I'm not understanding the exact question. So that is right. That mass, if you will go to heavier mass, but if you go to higher redshift, then effectively you detect lower mass. That is right. But what happens is that suppose there is a 500 solar mass black hole merger, which would be in TianGO if it was nearby. If it is at a high redshift, it may enter the Lisa band, leaving the TianGO band because it will be at even lower frequency.
Yeah, yeah, yeah. Okay, okay, yeah, thank you. Maybe these things will be more discussed when I will be talking.
You don't have the Hubble constant, right?
No, I mean these questions will be asked to me, or even I will ask these questions. Okay, thanks.
That is also fine. You can force questions in your talk.
Thank you.
This plot might give you a feel for to what extent the source localization would improve. I've shaded the bandwidth closer to the Deci-Hertz band. So over there, you can see that even for a source which is 200 megaparsec away, about 50% of the sources can be localized to 10 to the power minus 3 degrees squared here. And within 50 megaparsec, which would cover several galaxies. So that we almost have 100% detection, but even out till 200 megaparsec, we detect 50% sources with sufficient very good source localization. This is something I pulled out from the PhD thesis of Javed. So that the picture can give you a feel for how the sky is styled and how source localization can improve the way in which the source is identified in the sky. And this table can give you a feel for the neutron star source localization. Just by adding TianGO, just by itself, it can improve the source localization but by about 2 orders of magnitude. And then again, there is a question of where that detector will be placed. So if it's placed in the space orbit, if it is about 5 degree or 20 degree trailing, so I think that corresponds to I'm not sure if that's geocentric or heliocentric.
Yeah, heliocentric.
So that can take you all the way along with the ground-based detectors. It can take you all the way up to 10 to the power minus 6.
Go back to that. Can you explain this? I'm sorry, maybe I missed it. So the left hand side, not in the band, the best 50%, 90%. What does this mean?
So the solid line is your most confident detector. So if you place, so what they have done is they have averaged over the sky location.
How do you define that? Is it 90% average? Let me say angular uncertainty.
So what they have done is these are statistical blocks. They have averaged over the sky location and the source orientation. So to confidently say that we'll be able to detect this source at this distance, what they've done is they've taken a sample of sources, placed it at different sky locations, oriented them in different orientations, and then seeing what sort of signal will be detected with that detector. And then the best source is the one which will correspond to the strongest signal that your detector catches. The next, that is the solid line that you see, that is the best case. Then the 50% case is you detect 50% of the sources sufficiently strongly, and 90% detection is you detect 90% sufficiently strongly.
The distribution, it's a histogram. It's a particle histogram. Like the histogram around the best would be the
90% is like you're decreasing your SNR cuts kind of.
no, for the detected sources, 90% of them will have that code.
So angular uncertainty will be more for weaker sources. And for your best source, angular uncertainty would be least. So the solid curve is done.
You cannot give the best.
So I was this angular uncertainty, this is the sky localization area.
Right. So the best is the solid line. That is for let's say top 10%. Then it will be what?
So it gives megabars.
50 megaparsec, everything will be detected.
Lower, closer it is, uncertainty is lower.
So the 200 megaparsec is chosen because 50% falls exactly below 10 to the power minus 3. I think that's how. So this is where we are. I've covered early warning and source localization. Now to give you a feel for some of the cosmological prospects that can come about, they mostly deal with black holes, the cosmological process, because those are like the strongest signals, so cosmological distances would require black holes. So the first is gravitational wave cosmography. Right now that is being done using standard candle supernovae and the cosmic microwave background. But this will add binary black hole mergers as standard sirens. So you have a third independent test for gravitational wave cosmology. These two plots give you a feel. I don't know, that band.
Click on somewhere.
Go to the chair.
That was pretty good.
So the first plot will give you a feel for how the angular uncertainty will get better by about 2 orders of magnitude when TianGO is added to the existing network, and all throughout the parameters. And the second plot gives you a feel for how the distance can be measured independently without requiring any external calibration. So using the distance and the source localization, they also mentioned that even the Hubble constant can be computed. If you probably are even able to identify the host galaxy, then one can directly get the redshift as well. But these have the promise of having a separate instrument for gravitational wave cosmology, which are standard sirens. Next is probing the early universe using intermediate mass black holes. So first, if you see the plot, I've again shaded the Deci-Hertz band. You can see that both the TianGO curves peak in their sensitivity, where on the x-axis we have about 100 to 1000 solar mass. So those are binary mergers. These can be intermediate mass black hole with another intermediate mass black hole mostly, but one can even probe intermediate mass black holes with like a stellar mass black hole. So first, because of that kind of promise that the Deci-Hertz band have, it can provide completely conclusive proof either for or against the existence. Even a null detection would be very substantial in saying that we do not, we can say that ion gauges do not exist. Second has to do with cosmological large-scale structure formation. So the current idea is one does not know whether supermassive black holes arises from mergers of light seed black holes. So once intermediate mass black holes are either proved or disproved, one can place better constraints on these cosmological models. And since these light seeds arise from population 3 stars, which are your most early stars that form, one can also place constraints on the models of population 3 stars, which will not come from even JWST observation. So it can even go into that territory. Second, leaving cosmology aside, intermediate mass black holes themselves, even if they are in the local universe, can still be probed using the Deci-Hertz band. One, directly through the mergers, but second, when they are with a merger with another stellar mass black hole, that is known as intermediate mass ratio in spiral, so IMRIs, and about 1,000 are expected to be observed within a redshift of 1, and even that can provide good proof for whether they exist or not. And this can provide, especially because they're expected to happen primarily in globular cluster dense cores, it can provide some insight into the dynamics of those systems as well. Third is the type 1a supernovae, which you asked. This does not fall much in any other band. And the origin, these are standard candles. So again, this is how it can supplement cosmology. Type 1a supernovae are thought to arise from white dwarf binaries whose mass exceeds the Chandrasekhar limit. On the right, I have these plots. You can ignore the one below, I think, but the one above should show you how the frequency falls within the Deci-Hertz band, which is the full y-axis that you have. And it will be able to detect all subsystems to a large redshift and about a large mass range. So not only super Chandrasekhar masses, but also sub Chandrasekhar masses. So it can probe both regimes, which is also unique to this band. And not only that, because it's the Deci-Hertz band for white dwarf binaries, which is what you again asked about the uniqueness. So since it's a higher frequency compared to at the beginning of the binary evolution, you will have very low frequency. But then at the higher frequencies, you will have higher frequency evolution in case of white dwarfs. So that also makes the two components resolvable. I'll go into that later. But that is again unique to this particular band. But first, that from a cosmology perspective, it can completely have conclusive say on the double degenerate progenitor hypothesis for type 1a supernovae. So I think from the type 1a supernovae, what I would like to mention in this plot is the wide work binaries here. So they will give you some idea about the merger rates. And using these merger rates, if one compares it with the current theoretical calculations for the galactic population synthesis models, then that comparison can give you some idea about whether that hypothesis holds quite well. And last is the astrophysical sources and the corresponding parameters that can be derived from that. So first is your wide work binaries. Not only will they shine some light on the type 1a supernovae hypotheses, but they themselves can be studied to get some idea on wide dwarf physics itself. So first, tidal interactions are of two types: equilibrium tidal interactions and dynamical tidal interactions. The one relevant to this case is dynamical tidal interactions, in which there is excitation of waves within the interior of that compact objects. This typically arises and is required in this case because wide work binaries have much lower orbital velocity compared to black holes and neutron stars. So to get a feel for the mass ratio for those systems, one usually incorporates higher order post-Newtonian interactions, and which gives you an idea about the mass ratio, but that cannot be used for wide works. So the way that can be extracted from wide works is you have slow orbital velocity, and from the some of the energy goes in this tidal interaction. So because of the tidal interaction loss, about only 90% of the energy goes in gravitational waves and 10% goes in is dissipated away. So that accelerates orbital decay, and you're able to probe the frequency evolution much better, which is shown in this plot, I think. So this is the GW, and I've shaded the Deci-Hertz band again. So you can see as the frequency increases, an increasing portion of the GW radiation then goes into the dynamical tide. So dynamical tidal interactions become quite substantial for wide dwarfs. And over here, this is how the detector can actually measure those tidal interactions. The frequency shift can give you an idea for the energy which is dissipated away in those tidal interactions, because of which one can get some insight into the moment of inertia. And then that is extracted as a function of the component masses, so you can derive that. And then finally, one also gets insight into the accretion nature and the efficiency of the tidal coupling between that binary system. This table gives you some idea. Again, I've shaded the Deci-Hertz band. So you can see how the moment of inertia can be much better constrained by several orders of magnitude with frequency, because this orange curve is approaching the blue one.
So actually, Deci-Hertz comes from 100, but the detector will have sensitivity also in this band, so it should be.
Then the formation history of black hole binaries. The current models are degenerate, and the only conclusive discriminator that one has at this point is spin, measurement of spin, which is quite difficult. Although this is routinely, this has been attempted for X-ray binaries. I think the error bars are quite large in that case, but one would have to check. So these, the way they have described spin is with the help of two parameters. One is the effective spin, which is along the orbit. So it's coupled with the orbital spin. And then the second one is the precession spin, which is perpendicular to the binary orbit, orbital plane. So the chi effective is readily measured with ground frequencies, but precession spin lies in the Deci-Hertz band. So it is only the Deci-Hertz band that can give you a measure for the precession spin. And therefore, it is without this, one cannot have a 2D spin distribution of the black hole binary. So this is completely indispensable. And second, in case of X-ray binaries, one has high spin values, but with black hole binaries, what happens is because of the binary evolution, the actual spin expected also are quite low, let alone detected. So for this low spin values, the way even ground-based detectors are not able to constrain it properly. So the Deci-Hertz band can actually place much better constraints on the existing spin measurements as well. And second, because it's the only probe for the present.
So when you're saying that had equal mass or something? Because like if I think we measured where we have a symmetry, that can be right.
That is possible, that can be measured, but I think
What is the space?
when they are very close, if they are further away, I think then the precision can be more. Because when they are coming close, I think they get lost. The chances of alignment is more. There is some here like that. But when they have just formed, then suppose the binary has formed, I think this can be much more misaligned. So precision can be that is like it. I have looked at the people who are accurate.
That is what they say because of the locking.
Locking, that's what they're saying now. So because
I
of
know.
locking, in the end, because the matter is the ground based, they are more alike. But in the Deci-Hertz, they can be much more alike.
Because of that, this can provide an information on the formation history of the black hole binaries because you get an idea about whether that locking happened.
Yeah.
And the precession spin itself, even if it is detected, it can give some idea about the formation of second generation black holes, which again goes close to the intermediate mass black hole regime. And these are two plots. On the right, in both the plots, the right panel is the ground-based detection, and the left panel is the one with TianGO. So in both of the cases, the right panel is for the precession spin, and the left panel is for the aligned spin. In both of the cases, adding TianGO improves the spin measurement by at least an order of magnitude, and it is throughout the parameter space. So it's consistently improving the measurement. On the orbital eccentricity front also, which I think will be covered in a different topic, but this is another way one can probe the formation history of a black hole binaries. And TianGO, with its Deci-Hertz measurements, is the only one which can measure high orbital eccentricities, because most of the eccentricity gets dissipated away in gravitational waves in the ground-based frequency band. So if you see this plot, then we have LISA over here, and then even the ground-based with the Voyager design is over here. And if you think of them as fishing nets, then none of them really catch the signals, except the ground-based one is very sensitive to k=2, which is your quadrupolar for a circular orbit. So circular orbit will be detected very well in the ground-based, but TianGO is the only one which can not only measure k=2, but also higher harmonics corresponding to orbital eccentricity that get dissipated away before the orbit becomes almost quasi-circular and therefore do not enter the ground-based detector. So for such eccentric orbits, another difference is the k=2 component usually has a direct correspondence between the frequency and the time of the signal. But in the Deci-Hertz band, one will have multiple time frequency components arriving at the same time. But if these can be resolved, then one can measure very high eccentric orbits, which can form due to three different mechanisms which are stated across parameter space. And finally, this is the last promise. This is the detection of tertiary masses. Any modulation by a perturber bit might be present near the binary. So what will happen is the tertiary mass will modulate the motion of the binary at to or fro. So here I've shown an example of the binaries presented in the upper left corner. Suppose the tertiary mass is like a supermassive black hole. This is the case that they have considered. But some other cases they have considered is also two white dwarf systems and another exoplanet, or maybe a stellar mass black hole which is much close. So the tertiary mass itself is not important, but the perturbation which it can introduce in the system is important. So over here, for example, they have considered then a tertiary mass like a supermassive black hole can also have an accretion disk around it, and it can accelerate the rate of the mergers. If one assumes a circular and a coplanar orbit, then with Fisher matrix formalism, one would first have to compute the intrinsic waveform, and then the Doppler modulation can give you an idea for the tertiary masses which can be present around the binary. So this is similar to what I've done in my own graduate school project. So for X-ray binaries, but the only reason I showed you this second formula itself, the first formula is from the paper, the second one is for an X-ray binary. But in both cases, you have a binary orbit and you have a to and fro motion. And you can see how the frequency has a sinusoidal variation because of the binary velocity and because of the binary motion, basically. And the same thing I found in this paper as well, where that frequency appears in a very similar form. The phase is basically an integration of the frequency. So it's the frequency over here. And this modulation can give you an idea for any tertiary masses around it. However, there are other effects that one needs to account for, which I also had to account for because I had astrophysics. So you have to account for the motion of TianGO itself, add higher order post-Newtonian corrections. There's also some polarization info one can extract for it. And you have to account for the light travel times from the system to the barycenter of the solar system, and from the barycenter of the solar system to TianGO. So it's not a straightforward job, but this can be extracted. So finally, this is something I learned about recently. Coming away from TianGO and focusing simply on the Deci-Hertz band as such, one of the future prospects in India itself, I think, is thinking of launching one
Why did you
satellite.
get this?
What?
Take a picture.
Yes. Because it's not published yet.
This is not obvious.
So there are several questions which arise when one is planning a new mission like I'm proposing, but one challenge which really stood out for me was whether to place a satellite in a heliocentric or a geocentric orbit. And this picture was shown by Adhikari in that graph meeting, I think, and he also mentioned it's not published. So I've given an in-prep citation though.
And he
But-
says that it will be in archive very soon.
Yeah, he said. So the black curve gives an idea for the total noise. Here you can see, again, I shaded the Deci-Hertz band. Here the noise is mostly short noise dominated. So however, that is eliminated because it will be a space-based observatory. Here, however, the noise will be dominated by quantum radiation pressure, which I think they're also planning to optimize, as was covered in some of the previous presentations. But this gravity gradients part is something that still needs to be figured out. And that happens because of the low Earth orbit, I think. So there could be some gravity gradients introduced because of the satellite's motion around the Earth. So that needs to be thought about. I've put up some references. It was a very heavy paper. There were lots of references. Some of the references which stood out for me have been summarized in the first panel, and some which I added from my own side have been put down below. And I also noticed that some of the papers will anyway be covered in the next presentations.
It's very nice.